to, I'm going to record this and post it for those who are unable to make it. So if that's okay, I'll do that. And then also I need to share my screen, I guess. I apologize. I should have done that before. I guess it doesn't matter. I don't think there's much there yet. Let's see if I can find it for you. The data, it's going to be this political spectrum data. And I believe that's right here. So this will be the data set, the political spectrum, the political data. There's actually there's a political brand data set, and then this one here. And then, and I think you'll be using this primarily, this POL variable as your dependent variable. I think that's, yeah, I think this is the data set. And then there's a survey though that's also listed in Blackboard. And so the survey doesn't really, it goes more with the political brand data set than the data set you're going to use now. So the actual assignment for this week, I wouldn't worry too much about matching up the variables with the survey. They're not gonna sync up quite right, because the variables that you're using this week are composite variables that have already been formed and created for you. So so again, when you get into it, if you haven't looked at it already, if you're trying to match up what you see in the data set to the survey, it'll look a little hinky. It won't look quite right. And it's because there's been some composite variable work done already to the data set. So there's not a direct one-to-one kind of identification of the data to the survey. So let me know if you have questions on that, or throughout the week if you have questions as you're doing this assignment, for sure. We'll walk through some discriminant analysis and logistic regression tonight, just talk a little bit about it in general, maybe walk through an example or two of what it's all about, and then we'll go from there. So again, the assignment, if we go to the assignments page here and we go to logistic regression, discriminant analysis, again, there's sort of the assignment here. This first one, review the data for anomalies. Again, if you're trying to match the data to the survey, it's going to be tough to kind of do that. There's also going to be some idiosyncrasies with the data set. You'll see it where they'll see big areas of missing data. And so this is something that you should probably just be aware of in general. When you're doing, so this is like a semi-structured or a quasi-experiment type of a thing, where we have like 8 different scenarios, and I think it was 8, and the respondents were randomly assigned specific scenarios to look at. So they didn't, each respondent saw only 4 scenarios, not all 8. So in the data set, you look at the big data set, and if it hasn't been manipulated at all, you'll see where a respondent's, has answers for 4 of the scenarios, but then for the other 4, the data is blank or missing. And so in the Excel sheet or in a data set, you'll see a bunch of areas where there's just data missing, and it's simply because the respondent didn't see those scenarios. They weren't asked to look at them. They weren't asked to evaluate them. So, and that's part of the data management process. You kind of, if you wrote the survey and you kind of examined it and you did all the skip logics correctly, then you would see and you could match up your data set properly, moving forward. So that's going to be one of the things that you might look at or see, at least initially. And then step 2 of this assignment is we're going to do a discriminant analysis with the POL variable, and we're going to use very specific independent variables to help explain or help describe characteristics of these groups that are identified in the POL variable. So POL variable is a nominal variable. There are 3 groups in the POL nominal variable, and then the lib av, auth av, liberal av, and conservative av, those are composite variables, and those are going to be metric, of course. So we'll do a discriminant analysis first, and then we'll use the same type of data, use a logistic regression, run the logistic regression, and then what we want to do is use that information that we find from the logistic regression to predict group membership for those who hadn't been in a group before. So again, you'll walk through this. If you read the text for both those chapters thoroughly, if you follow the videos, I walk through examples for each of these, then you should be able to go through this assignment and complete it without too much trouble. These methods are not like factor analysis, which takes a lot of going back and forth and trial and error. And they're somewhat exploratory, but they're really not, because the groups that have been identified in POL are already identified. So that's something to know about discriminant analysis and logistic regression. The dependent variable in this case is the nominal variable, and the groups have already been predetermined or identified ahead of time. What we're generally trying to do is find variables that help explain group membership. We're not trying to identify groups. Those have already been identified. We're trying to identify variables that explain where an individual should fall within the groups that are there. So so this is a little bit less so you run the analysis and that's the analysis. It's not like you go back and try to do a lot of changing here or there. Factor analysis, you do a lot of that. Regression, you do some of that too, but these methods you probably do less of that. So it's a little bit more cut and dry. It's a little bit more of a cleaner analysis when you're running this. Okay, so that's kind of a preview for the assignment then this week. Just to stay on the same page while I'm talking about the assignment, I guess, we're kind of in this week 7, if you can believe it. That's actually amazing. I can't believe we're this far along, but we are. It seems like the summer is really, really going fast. I've heard from 5 of you for your topic of your method paper, and I was expecting to hear from you all this last week. So 3 of you I've not heard from. I posted again another post on what has been taken topic-wise for your method paper: conjoint analysis, correspondence analysis, canonical correlations, SEM, PLS SEM, and then multidimensional scaling for perceptual maps. Those 5 topics have been taken already, have been assigned. So touch base with me if you're one of the 3 who have not selected a topic yet, and let me know what you want to do. They're first come, first serve. So anybody have any questions so far? Okay, so again, we're in this week 7 period. We really held off doing a lot, or we held off kind of the face-to-face thing or the synchronous meeting like we're doing tonight last week, again, because these 2 topics kind of fold together and the assignments purposely put together into one. Because the techniques kind of duplicate each other. There's 2 ways to do a very similar thing. So, so chapter 7 and chapter 8, Module 4 and Module 5 combined together. I don't know, last week you may have already jumped into these topics together, or maybe you looked at discriminant analysis. Either way, be sure to knock those out this week and let me know if you have any questions, and then we'll just move forward throughout. Next week we'll jump into cluster analysis and then go from there. All right, good. Any questions so far? All right, let's talk a little bit then about some of these methods. And again, I'll try to walk through some examples. I just want to speak a little bit about kind of what we're talking about here. So when we talk about discriminant analysis, again, we want to think about groups of respondents or groups of whatever we're focusing on. So it could be groups of products, it could be groups of individuals, it could be market segments, or it could be competitors, it could be customers or whatever. But we're looking at groups that could be identified and grouped together on specific variables. Now, this is a deviation from what we've done in the past, because this introduces the idea of a nominal variable as something that we can use as opposed to a metric variable with our analysis. So there are certainly times, obviously, group data is nominal, and so we want to be able to use that. And so both discriminant analysis and logistic regression allow for a nominal dependent variable. So that's unlike what we've done before. So it's an appropriate technique when the dependent variable is categorical or nominal. It's non-metric at any rate. Independent variables, though, here tend to be metric, right? So I suppose you could have a dummy variable in the as an independent variable, and that would be non-metric, but I'm not sure you see that often. But anyways, we're typically looking at metric independent variables. Now with discriminant analysis, you can have multiple categories. So you could have 2, 3, 4 more categories. Once you get too many, that it gets really, really cumbersome. So more than 3 or 4 begins to get challenging with the data analysis and discriminant analysis. When we do logistic regression, you can only have 2. So if you have more than 2 groups, you need to use discriminant analysis. If you have 2 groups, then logistic regression may be conceptually easier to follow. I don't know that it's better one way or another, but you may use logistic regression with 2. All right, so again, as I mentioned, typically we're looking at groups that have been identified in advance. So this is not so much exploratory as it is, we know what groups we have because the variables are already defined for us. We've already collected data. We already have group membership. So individuals have already been placed into groups. Our goal here is, or the purpose here is, we want to identify variables that will help us discriminate between groups and group membership for the respondents. Okay, so when we test a model or a variate, the way we know it was successful was because it is better than assigning individuals by chance, if you will, or the pre-assigned randomness or pre-assigned responses that we already have. So we'll talk more about that in the example that I have. But what we basically want to do is we want to predict better than chance would that individual will be in one group or another. So that's kind of how we know whether we have success or not, by how accurate our predictions are in it. Couple other things mentioned just quickly here. So what gets created is it's a variate, or actually a variate for each group -1. So if you have 3 groups, there'll be 2 variates that are created. If you have 4 groups, there'll be 3 variates created. There are weights that are assigned to each variable, kind of like a beta. So think of it like a regression beta, only it's not. It's just called a weight, and it's actually designated as a W. And then there's something called a cutoff, and a centroid, and some other details like that, which we can talk about a little later, or you can review the videos on it if you want. But that helps us determine whether, again, whether an individual's in one group or another, how close they are to a group centroid versus how far away they are from a group centroid. Um, and um, and we'll talk about some of that stuff here in a little bit, I think. Um, okay, again, we want to predict. We eventually want to use these equations to identify group membership with predefined groups. Also, we can then, once we have the weights, use it as a predictor to predict unassigned members to groups as well. Yeah. All right. I'm just going to kind of skip ahead, talk a little bit about logistic regression here too. So we're kind of combining these techniques. So logistic analysis or logistic regression is a form of regression that only uses 2 groups. Again, dependent variable is metric, or is non-metric. It's nominal. What can we say about it here? Logistic regression is actually kind of interesting. I think you'll like it a lot, because what you do is you create a probability that an individual or respondent will be in one group, and if they're not in that group, they're in the other. So what happens is, we create the variate, and then we create a score for the individual, and then we transform that score into a probability. And you usually use a 0.50 for a cutoff. If somebody's above a 0.50, it means the probability of them being in group 1 is greater than 50%. And so we assign them to group 1. And if the probability is less than 50%, that they're in group 1, they automatically default into group 2. So conceptually, if you can think about like just assigning a probability based on a number of variables that an event will happen, then that's the way to think about it. So if you stretched back and you thought about probability theory and like just the probability of an event happening, and the event in this case is either you're in one group or the other, or you can really use this to predict all kinds of events, like somebody will buy or they won't buy, or just an event will happen or it won't. It's because it's a dummy variable. It's like a 1 or a 0. It'll either happen or it won't. Um, and then you can come up with variables that you think help explain why, something that will happen or won't. And then, that weight that's assigned to that variable kind of contributes to the probability of it happening. So, the mental work through of logistic regression, if it's really like a probability, and in fact, there's something called probit models as opposed to logit models, which are exactly that. They're the probability of events happening. So logistic regression, then it's a little bit different in terms of how you kind of think about it, but the end result is more or less the same. Again, for logistic regression, the dependent variables like this binary, because you only have 2 options. So the error term has a binomial distribution, not a normal distribution. So as a result, if you think about some of the assumptions that are required for regular regression, we're going to violate those because we don't have a normally distributed, the error terms are not normally distributed for that specific variable. So that's one thing to think about. And then also heteroscedasticity, the between the dependent variable, the relationship between the dependent variable and independent variables vary inconsistently over 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 a range of values. So so anyways, those violations of assumptions need to be absorbed somehow, and logistic regression is pretty robust. So so it's something that you can you know you could actually, if you were having trouble with a regression because some of your variables didn't meet these criteria, these assumptions, you could actually create binary variables or dummy variables, and maybe run your analysis as a logit model between groups as opposed to using metric data. And that might be something that you could do if you're having data problems. So you might be able to adjust and not use a regular regression, but switch your data around to be binary for the dependent variable, and that may work. So anyways, again, not to get too deep into the weeds tonight, because your text will, and you can, as you're reading through this, you're going to kind of think about the variates a little bit probably, and kind of commit some of this to memory, I would guess. But the variate for discriminant analysis has, as I mentioned, these W's. The W's are just simply called weights, and they come together to form a score, which is in this case in discriminant analysis a z-score. It's not the same as a probability z-score. It's a different thing. They just denote it as a z, um, and that's what it is. So the z's then are values or scores that are then placed on individuals as they either group. And these W's are actually going to be distances that that can be applied. So distances from a group center versus distances away from another group center, and so forth. So again, this isn't a math class per se, so we're not gonna go into too much detail there. The other kind of mathly related thing on the logistic regression side deals with two functions which are actually pretty important: a g of x and a pi of x, or a p of x function. So the g of x function is what we'll end up calculating, which then needs to be transformed into a p of x, or a probability, which is what we end up with. So this is what we'll actually evaluate as, when we do the g of x, it'll be it'll be a linear combination of the weights that are, or the betas that are created from the regression formula, that you're used to seeing. But then we'll transform that into a probability, and then the probability will fall between 0 and 0.00 and 0.1. So it'll be like anything above 0.5 would be that greater than 50% idea. Anything less than 0.5 would be less than 50%. So if something scores higher than 50%, if the p of x is greater than 0.5, then we're going to say it's likely to happen, the event, whatever it is. If it's less than 0.5, we'll say it's not likely to happen, and we'll say the event won't happen if that's the case. Okay, so again, this is all kind of in the videos. Again, if my videos aren't particularly clear or whatnot, feel free to look at others. This material here is really common. I mean, it's not, this is not material that is only created for this course. There are lots and lots of courses out there that cover logistic regression and discriminant analysis. So please feel free, I encourage you to find resources that maybe, talk about this in a different way if it helps you. Okay, so with that, let's talk a little bit about, we can do some examples here, I think, and tell you what I'm going to do. I'm going to do that first. Sorry, I had to clear out of a couple things. We'll look at the packaging data. Okay, so this is a data set you don't have, but it's one that I just pulled up earlier, and I wanted to see if I could do some analysis on it. This is a paper. This is a data set that was collected a couple years ago, and what we're looking at deals with unusual package design. So like if you have a product category and within that product category, somebody creates a packaging design, even if it's like a temporary promotional package, but it's a package design that's unusual or unique or incongruent to the others in that product category, unexpected, then that unexpectedness and that incongruity will create some tension. It'll create some interest. It'll create some curiosity and things like that. So one of the ideas of this research project was to simply kind of create a model that looked at whether package design positively impacted, and to the extent that it positively impacted emotional reactions to products. And and it kind of unsurprisingly it does. You have this kind of reaction where the respondent could look at the package and just be confused or dismayed, or find some type of like dissonance or something like that, and it could turn them away, or it could spark kind of an interest or a curiosity, and they could find it novel and interesting, and that could draw them closer. So anyways, it's like the emotional connections that are formed when people see things that are unusual or unexpected in a packaging realm. So that's kind of, so you'll see sort of the variables here. Um, and again, this was basically what we did was we did a pre-test, and we did a pilot study to create or to establish incongruency levels for a series of 16 different products. These were real products, product packages. And then we brought in groups of consumers and had them hold and evaluate the products that we had, and then score each product on how they felt on these different emotional states. So it was a little, I don't know that it's the greatest experiment in the world, but the data came back, and we have a bunch of it. So it's worth at least looking into. So these variables here are the ones that kind of show how a reaction to the product. So somebody would pick up a product package, and then like one of the questions asked whether they felt like they were more attentive to the product, whether the product kind of drew them in emotionally, if they were interested in it, and so on. And then there are a bunch of emotions here like curiosity, anxiety, being excited, and so on and so forth. So those are kind of the variables that we'll look at. And then what we're going to do in this is we've got 3 different product categories. Oops. We're going to do product category here. We're going to look at 3 specific product categories, and we're going to focus on products that were in an alcohol category. So like Bacardi, and I think they were mostly hard liquors like Bacardi and rum, and Bacardi is a rum, and there were a couple of vodkas, and I can't really remember all of them that were there, but some of the products were in the alcohol category. Some of the products were candles in a candle category, and then some of the products were in a jewelry category. So we got 3 different product categories, and the question here, I guess is, are there variables that we can use that would indicate product category, and define. So if I had a product, I suppose if I wanted to put a product in, say, the candle product category, there would be certain variables that you'd typically see in that type of product. And I suppose you could say if I wanted to be different and incongruent, then I would adjust what you would typically see in that product category, and I would create a product package that was different and unlike what you would typically see, to creating congruence. So, and then measure the effects probably of how that would be. So, so we could go from there. So I think that's what we'll do. And I've already done some of this already, but basically this is going to be our dependent variable. We have 3 groups. Again, these are nominal variables. There's not kind of like an implied order at all. It's just a 1, 2, or a 3 that's there. And then again, we'll use these other variables here just to see if we can have some of these make sense or help describe what we're doing. Okay, so so with the discriminant analysis, we go to analysis. We're going to go into classify. Just so you know, in another couple weeks, or another week, I guess, we're going to do, next week, I suppose, we'll do cluster analysis. So we're going to use these guys in cluster analysis. But tonight, we'll do discriminant analysis. And so we're going to do that. And oh, we'll pull over the dialog box. Now we can enter all the variables together, or to make it a little cleaner and easier, a lot of times we'll just kind of skip to the stepwise method. So you'll remember this is akin to what we did in regression analysis. If you want to use an entry method that takes one variable at a time and excludes variables for you that are not very explanatory or not helpful in your analysis, then you can do that. The other thing that I'll add is I have not gone to great lengths to double check for outliers and things like that. So that, yeah, outliers are actually going to be an impact on this analysis. So should probably do that, but haven't quite gone to that. So anyways, I've got these independent variables that I put in here already that came from the data set. And then I also have my product category dependent variable. One thing to remember for this is that you do need to specify the range. So these are the actual numbers. Like in that variable, you could either have a 1, a 2, or a 3. And 1 meant one category, a 2 meant a different category, and 3 meant a third category. So 1, 2, and 3 is, and so that's an important thing if you're setting up your data set, that they're coded correctly. Your groupings are coded correctly. So that's there. And again, remember, I already have my groups assigned, so I know what was what. I know what observations fell into each of those groups. So those guys are there. And I'm going to do this, when I run this, I'm going to run it with all of the different boxes you would probably checked, which means the output's going to be really long, and it may be too much, but anyways, that's kind of what we want to do. Yeah, okay, Fishers, make sure you check the Fishers box here. It'll give us the proper coefficients that we want to use for creating variates or for predicting values later. So that's something that we want to make sure we do. Okay, those are generally good. Okay, now this one here, method relates to the method that we chose. Oops, that we chose here. If we did the enter method, then we wouldn't get this box, wouldn't have this as an option, but we chose a stepwise method. And so again, what's going to happen here, not to get too deep into the, make it too abstract, but we're going to look at each respondent, and we're going to look at the software is going to create a group center, statistical group center for the variables that are provided. And then it'll look at individual responses, and the ones that are closer to that center will be grouped together, and the ones that are further out from that center will be grouped with another grouping in another group. So the question here is, if you have a center and you have a respondent, you want to be able to calculate the distance between the center of a group and where the respondent is to determine what group they're in. And so how we determine that distance is kind of the method. And so we've used this Mahalanobis distance before. And again, it continues to be a robust method for us to use here. So it's suggested that you go ahead and you continue to use this as a distancing method to calculate the distance between the respondent and where the center of a group is, so that we can identify which group they'll be in. Okay, summary of steps. Again, this is going to create a lot of information that may or may not be helpful, but it'll be there. You may not do that in the future. And pairwise distances I'll mention briefly as we go forward as well. It's helpful, but semi-helpful. It's not like the end of the world. All right, other things. So certainly some plots are fun to do. Territorial map is really helpful. It's good to be able to report and look at. If you've not decided on a missing data imputation method, you might choose to replace with the mean here. If you've already done it, then great. Something along that's perfectly fine to be able to do. I think, I can't remember, but I believe that the groups are fairly evenly distributed. But again, if you don't have exact even numbers, it's sometimes not a bad idea to compute from group sizes for the prior probabilities. And we'll look at that specifically because we want to know like what the current probability rate would be if we just went with the groups we have versus our predictive availability of our model. So we want to be able to kind of look at that specifically.
Dr. Flight, I
Yeah,
have a
yeah.
question. So for our assignment, right, you said there's going to be a lot of like missing values. I wanted to know if we're supposed to check this box for it or just like leave it.
So the way I set up the data set is
Yeah.
that so the variables that you use are composite variables,
Okay.
and there shouldn't be any missing data in those composite variables.
Oh,
The
okay.
missing data is further, it's earlier in the analysis. So if you just do a visual inspection of the data, you'll see like some blank spaces here and there because of that. But if you look at the columns that involve the variables that you'll be using, those should be complete.
Okay. Got it.
Yeah, I don't think you'll run it. So you can click that box for sure. But again, the problem you're specifying, I don't think really exists, only in those variables. And yeah, you should be okay.
Okay.
Great question.
Thank you.
Fantastic question. Again, I think this is good for right now. We'll continue and we'll look at, should we do, so you can definitely check these boxes on predicted group membership if you want, discriminant scores. So these are going to create new variables for us. And sometimes I run analysis quite a bit before I ever do any type of save, because every time you save, you're going to add variables to your data set, and it sometimes just gets confusing. So you could choose not to save anything if you want, or you could do this. That would be fine. That would be fine as well. So we'll just do that. And now we're going to run OK, and we're going to see what happens. So anyways, you're gonna get a whole bunch of data here. We're gonna come down to a couple charts and a couple graphs down below here eventually. You know, the quick thing just to visually see this chart here, and this graph, excuse me, here, will kind of indicate this idea that we've got three different groups. And those groups, I don't know if I can get that any bigger or not, probably, but those three different groups have centers, and certain variable or certain responses kind of group around those centers. So the responses that were categorized as alcohol products should circle around and group around the alcohol center. The jewelry, which are the green here, should circle around that jewelry center. And then the candle ones should center around there. Now you'll notice like there's a green spot up here, there's a red spot here, and like blue spot here. Those may be outliers. And so as you can imagine, if you have some outliers here that just seem to not fit the norm, they could really kind of impact where those centers are and the predictive ability of the overall model. So again, I didn't do really a lot of work here before the class to clean up the outliers, but you probably, want to do that just to get, a cleaner result if possible in this particular case. Okay, but that's kind of that chart. Let's move back up because again, I just, that's kind of the fun thing to look at. So I like to look at it. We have 348 respondents in this particular data set. So this box here may or may not be helpful. We have a lot of variables. So what this gives us is the mean of each, the statistics for each variable, the mean, standard deviation is really kind of what you want to look at by dependent variable. So the mean of holds my attention for alcohol is 5.7. Come down here below, the mean of holds my attention for candle is 5.2. The mean for jewelry on hold my attention is 5.3. So kind of visually, you can start to look and just kind of see what these means look like and see if there's distinction across groups on some of these variables. This would be kind of a preliminary look. Again, this is a big list of independent variables, so it's a bit cumbersome. The other thing you can do is you can start looking and seeing how many are in each of these categories. So we have 115 respondents in alcohol or evaluations of the alcohol products. We have 113 evaluations for candle and then 120 for jewelry. So those aren't perfectly balanced, but they're pretty close. I mean, they're not that far off. I mean, generally you want I think it's 30 or 40 or so in each category at least. And then kind of some balance is nice. It's not required, but it is nice to have. And that works out pretty well here. So, all right, we've got a bunch of variables, a bunch of things there. This box is a bit more helpful because it takes your independent variables and it kind of gives you like an ANOVA. It is an F-test where basically what it says is if I've got a variable, can I find or am I finding some statistical difference between the means between these groups? So I've got three groups. I've got a mean for each group on each of these variables. And the question is there statistical difference between them as a, kind of in a collective group? And so if it's significant, it's significant. And a lot of these are. Dread is not. Embarrassed is not. Miserable is not. These last few are not. But some of these others certainly seem to be quite significant in that there's some distinction or difference between means across each of these three groups on these variables. So that's good. That's an early indication that says that I've chosen some variables that help discriminate between one group and another. That's what we want to do. That's our goal here. We want to find the best fitting group of variables that help us in a parsimonious way, kind of explain group membership. So, so then because we did a stepwise approach, what it means is we're going to have a series of steps. And each step in this particular case means that we're adding a variable and it's going to add the strongest variables first in order to help explain group membership. Okay, so step one, anxious. Step 2, sentimental, nostalgia, and so on and so forth. So each step, it's basically running a new model by bringing in a variable that is said to help explain group membership better, until it doesn't. So in other words, in this particular run, we had 8 variables entered in. The 9th variable did not contribute to the predictive ability of the model. So it doesn't do any more after that. So in other words, there are no other variables in this analysis that contribute better to the model than those that have been chosen. So again, that's fantastic for us because we kind of run the analysis. We've got 8 variables. That's super. It seems like it's a good thing that's going on here. This significance gradually gets smaller and smaller and smaller as it goes, and that's, you know, kind of what you would want to see. Okay, so that's kind of that's where we are. Yeah, variables entered, and removed. We've got 8 variables entered. This analysis. Yeah, okay. So this is this last model here. Again, if you want to know the variables that are not in the analysis, we have a chart for that. Again, not very helpful to us at this particular point because these are things that are not used. They've been discarded at each particular stage. So if you print this out, you're going to be killing a small forest without a lot of benefit. The Wilks Lambda table here essentially tells us what we saw before for each of the 8 models. This lambda value will be going down. The significance will actually be going down. And that's all good. I mean, again, it reaffirms this idea that we have a significant overall model. So that's kind of what we want to do. Now, one thing that we don't know, we know that there's difference between these groups and the dependent variable on the means for each of these 8 variables, and that these 8 variables contribute together, don't overlap each other too much in explaining group membership. One of the boxes we checked was for a pairwise group comparison. So like an F test or an F statistic, like in an ANOVA, gives you the entire model fit. And that's great. But a lot of times we want to know, like, within items in a model, or in this case, within groups within a model, whether there's significant difference between the two. And so the pairwise group comparisons gives us that. And what we do with this box is we look at the very last model, because that's the model that we're going to retain for this analysis. And what it does is it does sort of like this individual F between each of the groups that are being analyzed. So as opposed to a global F for the whole model, this is like 3 separate Fs between groups. Again, we've got a lot of distinction going on between these 2 groups with these 8 variables that we found. These 8 variables really distinguish these groups well, or well enough. So these are all significant. But if you had 2 groups that were really close to each other, it might be that one group was far apart and the other 2 groups were close to each other, and they may not be significantly different from each other. And if that was the case, then you may consider just grouping them together as one. So anyways, be that as it may, we have 3 distinct groups that discriminate from each other, both in a global sense, but then also in this pairwise model or box here as well. Okay, a couple other things that we're going to look at. We want to come down here. There's going to be two boxes that you may look at: the standardized canonical discriminant function coefficients, and then down a little bit lower, this guy right here, the canonical discriminant function coefficients. So you'll look at these two and they kind of would remind you of factor analysis. Like I mentioned before, you know, if you think about factor analysis and this idea that you're kind of grouping variables or whatever, then that might be what you're doing. In this case, we're looking at variables and how well they kind of explain, or a variate that puts them together in explaining group membership. So so I mentioned that we have a variate for each group in the dependent variable area -1. So we have 3 different groups in the dependent variable: candles, alcohol, and whatever the third one was. I should know it off the top of my head, but we got 3. 3 minus 1 is 2, so we have 2 variates. So what's going to happen here is the software is going to create this variate, and the variate number 1. And what they'll do is it'll like assign a value. It'll run each response or each observation on variate number 1 and create a score. And it's like that Mahalanobis d squared or Mahalanobis distance. And it'll look at that distance and it'll say, well, look, if this observation is close enough to the center, so we've got we actually have these, we actually have these centroids, these centers. If this observation is close enough to the center, we're going to say it's in group 1 based on a cutoff. If it's not inside that distance, it's not in group 1, so we're going to run it on function number 2 here, or variate number 2. So it's like a sequence that's going to happen. We'll take all 348 or whatever observations and get a score on function 1. And any of those that fall within a minimal distance will be categorized as a 1. Anybody who's not will be sent into a different group. We'll run the second function on those who are not 1s. And again, we'll do it again. Any of those remaining observations that haven't been a 1, that are within a minimal distance to the group centroid, they'll be designated as group 2. We'll go through all those observations that had remained after identifying group 1. And then finally, anybody who's not a 1, anybody who's not a 2 must be a 3. So there's really no reason to do a third function, a third centroid, or a third weighted variate, because if you're not a 1 and you're not a 2, you must be a 3 in this case. So that's kind of what's going on here. So these canonical discriminant function coefficients, these are the W's. And these are what we use to measure or predict future group membership moving forward. So again, you use like a regression formula and you use the betas, the non-standardized betas, to predict, like future dependent variables to predict, right, what that'll be. Same thing here. We're using these functions, this variate, to predict group membership, and we can moving on further on. So these are things like you would record, and then as you do analysis and you do other projects down the road, if this model holds, you can continue to use those. All right, so cool. So that's my variate. Those are my variates that I'm using. The other thing that we're going to look at here while we're talking about it, we're going to talk about prior probabilities, and then we're going to talk about classification. Okay, so the prior probabilities, you'll just look at this and you'll say, well, look, 115, remember these numbers, 115, 113, and 120. Those are the respondents, those are the observations that fell into each of these groups a priori. So before we did our analysis and all, we already had group membership. Well, remember, we're looking for variables to show group membership. We already have our group membership, and this is what it is. 33% of our respondents fell into or our observations were on the alcohol product category. 32.5% were in the candle, and then 34.5% were in the jewelry area. Okay, so basically what we want to do is say, well, look, this is, and this is like, I mean, this is not a particularly high threshold to say you had success, but this is what the way it is. You look at that, and there's roughly what, 33% or so. If you average those together, probably 33% is like a benchmark thing. You know, if I was able to predict group membership better than 33%, then I'd say that my variants are good. So there's actually a benchmark of 25% better. That's basically what it is. Like if you said your model was 25% better than chance or 25% better than the base, then what we would do is we're going to look at like 25% better than each of these. So like if alcohol is you know, I have a 33% chance of drawing an alcohol product category by chance, then 25% better would be 1.25 times 33. So we're talking 41.25%. So if I can predict, you know, membership into that category better than 41.25%, then this is said to be a success. Okay, so again, not a high threshold, but that's what we do. So you need to know these before you get going. You know, you can use this box, or you can simply divide your group membership by the total and get these percentages. And then what we're going to do is we're going to drop all the way down to the bottom of the analysis and look at our classification table. Okay, so we're going to drop all the way down and drop below there, below our pretty graph or chart, yeah, graph, I guess. And we're going to look at this classification result. So using the variate that was created, the software went back in and created a score for each observation, determined an appropriate cutoff, and then placed each respondent as either an alcohol product, a candle product, or a jewelry product. So this is like a validation process. And so this is one of the things that you want to do, is you want to validate your model. And so this is one way to validate your model. Another way you could do this is to run this analysis on some of your data, get your variates, and then go ahead and calculate your variate score on the data you didn't use and see how well you predict. So you can do a holdout sample, in other words, to achieve this as well. And that's probably a better process. But anyways, the software will go ahead and it'll run the analysis, it'll classify your groups, and then it'll tell you how well it did. So if you look at this, we've got two different parts here, the original and then the cross-validated part. The cross-validated part has one extra step, which helps be a little bit more valid, I guess, in terms of whether your model works well or not. So it'll be a little bit lower. It's a little bit harder to achieve, but you're still going to be fine. So basically the deal here is what we're going to look at is these percentages as they relate to each category. So if I looked at alcohol, 60% of my alcohol product category observations, 60% were categorized correctly. Now remember, we just saw the prior probabilities box, and it said 33% would be appropriate, or would be random. You know, if we just randomly picked groups and put them into alcohol, we would have been right 33% of the time. This is saying that if I use my variate, I'll be right 60% of the time. And remember, our cutoff for a good model was 25% better, which was 41% or so. So clearly we're doing better than chance. We're doing better than what we would say a minimal expectation would be if we're predicting 60% of the time group membership for this category. For the candle, we're going to drop down here and look at this percentage, 58%. So 58% of the time, we're predicting correctly that a observation would be a candle product. And then for jewelry, we've got 66.7%. So again, much better. Um, Again, if you checked the cross-validated option, that which is better to do, you'd follow the 54% that's down here, the 54.9, and then the 65.8. Again, it just adds an extra step and makes the test a little stronger to validate whether the model is running or predicting effectively or not. So down here we have 61.8% of the original grouped cases were correctly classified. Now, obviously, we want to continue to refine our variables, add variables, modify variables, do whatever, what we think will increase this percentage. Our goal is to, increase the percentage as high as we can in order to be able to, predict group membership moving forward. That's, kind of the thing that we want to do. Okay, but that's discriminant analysis, and that's, there's a lot of nuances here. There's a lot of little bits and pieces, and I'm not really going into it all, kind of like a lot of the technical detail stuff, because that's okay. What I want you to be able to do is run the analysis and interpret what you see, interpret the variables, be able to distinguish groups, and kind of go from there. Okay, so all right, questions on discriminant analysis so far? Has anybody tried or attempted discriminant analysis? Homework assignment? Not quite yet. That's okay. It's all right. Jump into it. You'll have fun with it. I strongly again recommend jumping in with the textbook. Textbook stuff is always good to do, and see how that goes. Okay, so shifting gears then slightly. Let's look at logistic regression. Logit models are fun to do. I've always enjoyed them, and I don't know why. Call me crazy, but for some reason I've always enjoyed the whole logistic function idea. So I've got another data set here where we'll do. I think this is the data set. We'll do a Logit model. We'll just see what it's. So remember, with a logistic regression, your binary, your dependent variable needs to be binary. It needs to be either a 1 or a 0. It can't be multi-group beyond 2. So discriminant analysis is appropriate for a three or more group analysis. Logistic regression is not. So with that other data set, it was going to be kind of a hassle for me to try to create a 2-group variable without too much strife. So what I did was, I've got another data set here. And this data set, let me give you a little bit of background on this. This is a B2B, or a business level type of a data set, where the observations are from managers who are running a business, a small business, and they're talking about kind of their orientation towards how they do business, like whether they focus on the customer a lot or if they focus on a competitor a lot, their view on risk, whether there's a lot of uncertainty, their views on performance, and so on and so forth. So this is a little bit of a different data set. Again, the observations are companies, and we have, let's see here, there's 150 companies in the data set. Not all of them have answered the questions, though, that we're going to use. So the full data, so the data that we're going to use, I think it's more like 112 or something like that. And what we're going to look at is a strategy, a way to describe businesses in terms of a strategy. And so this is something that you may recall from a marketing class or a management class, really. Um, I think this was like in 1960 or something like that. Miles and Snow created a classification system for for firms and kind of how managers, how firms operate. And the typology they created um, kind of came down to four different like ways companies operate, or view them, view competition, and kind of enter markets and stuff like that. So the classifications were prospectors, defenders, or are prospectors, defenders, analyzers, and reactors. And so as it turns out, there are very few reactors. And it's just not something you would typically want to be. Just as a snapshot here, again, to give you some feedback, if you're not familiar with this typology, a prospector is somebody who is very aggressive in the marketplace, very innovative, always looking for new opportunities, willing to accept a lot of risk. Um, Here, they competes primarily by stimulating and meeting new market opportunities. So they may experience a fair amount of failure, but for every, 5 failures they have one success, and so it's a typical innovator, first mover type of a character. The defender is somebody who has a product or has a market that they feel very comfortable with, and they want to dominate that product category or that market space, and they want to, as the name implies, defend their position vigorously. They don't necessarily want to jump out and create new products and do new things, so they're not necessarily innovative, but they're very territorial. So they'll manage their price, they'll manage their product, they'll really look at CRM a lot to really foster strong customer relations. But again, not be as innovative as a prospector, but very defensive. So they might be in a niche, they might be kind of category dependent or specific with kind of how they do business. The other two, the analyzer and the reactor. So an analyzer is an intermediate type. They make fewer, slower product market changes than prospectors, but they're willing to move around the game board a little bit more than defenders. So if you can kind of think of them as less innovative than innovators or than prospectors, but more flexible than defenders, that's kind of who they are. They will jump into a good opportunity if they see it, but they've got to do a lot of precautionary work to make sure that's what they want to do. So they're more deliberative, they're slower to react, but they will react and move outside of a product category or a customer base if it's advantageous for them to do so. The reactor is kind of this business character who is last to everything. Like they're the last ones out of a product category. They're the last ones to adopt a new technology. They generally get pushed into change by the marketplace or by competitors. They're not leading, they're following. So again, that's one reason why very few companies actually identify as reactors, because it's not usually a very positive type of name or description of a company. Okay, so this data set then looks at these four categories. And we actually ask people in the survey to define themselves or describe themselves a couple different ways. And I'm just kind of looking for those variables. We have these different variables: Miles and Snow type, and then we have defender, reactor, prospector, and analyzer. So we actually ask a couple different ways. We describe the four types, and we ask people to indicate which of them they are. Are they, a defender, whatever, prospector, or whatever? And so 1, 2, 3, or 4, that's what this is. Then we also ask a different way. We ask on a scale like to 1 to 7 or something like that. Where are you on these four different, types of businesses? So anyways, that's kind of how the data is set up. But what I did just for this exercise is I created a new variable where I combined a couple of these types. So I have this where the defenders and the reactors were combined together, and they're labeled a 1. And again, we've got some missing data here, which won't be included so much in the analysis because it's the key variable. But these guys here will be labeled the 1, the defender and reactors. If you're not a 1, you're a 0, which means that you would either be a prospector or an analyzer. Okay, so because prospectors and analyzers probably are most closely aligned with each other, reactors and defenders are probably most likely aligned with themselves. So basically what I did was I took the 4 categories and I consolidated them into 2 so that I have a binary variable so that I could do logistic regression. Okay, so it's either going to be a 1, who's a defender or reactor, or a 0, and that would be a company that's either a prospector or analyzer. Okay, and then I'm going to throw some variables in there. I've got a whole bunch of variables in this data set. I have some composite variables, but then I have all of these other variables that measure things like risk aversion. So I've got a bunch of risk aversion questions. I have the eyes here deal with interfunctional coordination, whether they, in other words, whether they communicate internally well. We have innovation orientation, so if the company's innovative or not. All those variables. We have performance outcomes and so on and so forth. So we've got lots of variables actually to choose from. And again, this is just kind of an example, so I'm not going to go into huge kind of like analysis on what each of those variables are, but we're going to run into regression. And under regression, we're going to go into binary logistic. So that's something we hadn't done yet. We're going to go into binary logistic, and then we're going to set it up. So for this, and again, this is like that second part of your homework assignment, I've got my dependent variable. Remember, it's either going to be a 1 or a 0. So there's no need here to specify like levels or anything like that, or a range like we did in discriminant analysis, because it's either a 1 or a 0. And then I've got a whole bunch of dependent variables or independent variables here. I've got those performance, I got innovation orientation, just got a whole bunch of stuff there that I just threw in there to see what would shake out. A big suggestion here is to use the forward walled entry method. So this is, again, it's a type of stepwise regression, but the research suggests that a walled entry method, and it's just a name, works well for you. So please consider doing that. Again, if you run this as a enter method, you're going to have a lot of cumbersomeness that you'll have to overcome. So you may not want to have to deal with that. So this is actually, if any of your independent variables are categorical, then you need to identify them as covariates. We don't have any, but again, if any of the variables that we put inside this independent variable area, if any of them were non-metric, in other words, if any of them were nominal or interval, then we would identify them as categorical covariates. So again, don't worry about that in this analysis. I don't think you have to worry about that in your assignment either.
Dr. Flight?
Yeah.
I have a question.
Yep.
What is the difference between the forward and backward? I mean, does it just, it's like ascending and descending kind of a thing?
Yeah. So depending on the analysis that you run, the type of analysis or the method that you run, one method, it's like backwards or forwards. It'll it'll like run all the variables at once, and then each step it'll take the least performing variable out, One of them will do that. I think that's probably the backward one. Forward stepwise regressions will, or the other stepwise regressions will take your strongest variables first and then add to it. So in other words, one method uses all the variables in block one and then takes variables out as it deems appropriate each step.
Mhm.
And then the other one works in the reverse order. It adds variables, starts with one and then adds to it. So for instance, in the discriminant analysis, the first model that was run only had one variable. The second model that was run had two variables. The third model had three, and so on until we had 8 variables. So that's like one method. Another method might be where all the variables are put in all at once, and then sequentially one is taken out as the least performer until the best set is accounted for.
Okay.
And I would say this for a lot of these, to be honest, is it doesn't cost you anything other than some time and effort. If you want to try and just experiment and just see what type of results you get, kind of running different entry methods, you absolutely can do that. And you may find one entry method produces a better predictive model than another, and that's okay. And so feel free to be flexible, feel free to try. And while WALD oftentimes produces the best result, may not always, and so that's okay. Does that
Thank
help?
you.
All right.
Yes.
Super.
Thank you.
All right. So some of the options here, the save function or the save area here, you'll want to check probabilities in group membership eventually. Again, you may or may not want to do that now, but you can if you should so choose. I've done that already, so we may have some extraneous variables that don't need to be there, but are there. The Hosmer-Lemshow goodness of fit test is what you want to do. You may check case-wise listing of residuals if you have not done an outlier analysis yet. So that may be something to check as well. Generally, you want to keep a constant in the model and then kind of go from there. Style, I don't think there's nothing we want to do with that. So again, we're, it's like the analysis we're running, we got these variables, there's a little trial and error. My goal is to find the best variables that are gonna like predict whether somebody is, or whether a firm is going to be in group 1 or group 2 in this particular case. Again, think of this grouping method as an event happening. So like a 1 is the event happened, a 0 is the event did not happen. And then if you think of it that way, you can use this as an analysis for like a purchase history, or some type of like action or decision being made or whatever. It's very flexible. You can use this in a lot of different ways. Okay, so we'll just click OK. And again, we've got a whole bunch of data that's gonna come up here. So I'm gonna head to the top of the logistic regression just so that we can case processing summary. Okay, and again, there's a whole bunch of missing data because I had respondents not fill out. So I might have told you guys this. This was that survey that was paper and pencil, and the backside of the survey, backside of the paper had survey questions, and I had a bunch of respondents not answer those because they didn't realize there were questions on the back of the survey. There were 35, and that's where these come from. So it was a kind of a screw up on my end because I didn't anticipate respondents wouldn't see the back. And so anyways, that's a big artifact. And, like what I'd want to do is I'd want to analyze those who didn't respond to those who did respond and deal with it that way, probably for the missing data. But anyways, this analysis will run on 115. Again, we've got the dependent variable encoding. So a 1 should be the defender reactor, a 0 would be the prospector analyzer. And that's the way that was. It's going to do a forward walled. So it's going to do step 1 or step 0 is a model with it's just a blank model with nothing. So we're not going to really worry about that. We're going to move more towards once we start entering, you know, entering variables, entering variables into here. Let me just. We do have some variables that end up identifying as significant in here, but not all of them. We have an overall model fit. It looks like we'll have 8 or 9 variables in there. The Nagelkirk R squared is kind of like an R square that you would use for like a regular regression. The bigger the better, right? That's kind of what you want. This will go up in value. The 2 log likelihood value will go down. So we're approaching good models here. You know, it sure seems to be anyways. So we're happy with that. We asked for the Hosmer-Lemshow test. We're looking for something above 0.5. That's kind of the cutoff. And eventually, and again, we're going to see lots of variation here until it has a best fitting model. So we're above 0.5. So that seems to be adequate there. Again, we're going to drop down. This table's a little interesting, although, you know, we've already been told it's an okay fitting model. We're going to drop down to the very last piece here in the very last iteration or row here. And what you want to do, which is confirmatory, is see that this number, the 0, is relatively close to this number, and the 7 is relatively close to that. So that's super good. That's what we want to be able to do. And then we run into this classification table. So, so again, you know, what we're doing is we're creating a variate that gets converted to a variate score for each of the respondents that then gets converted to a probability. If the probability is above 0.5, then it's classified a 1. If its probability is below 0.5, it's classified as a 0. And so this classification table suggests that for 44 of the cases that were prospector analyzers, the model accurately predicted that they were for 44 times. So 77% of the time, the model accurately predicted prospector analyzers, and close to 80% of the time, we predicted defender reactors. So that's good. 78.3% of the time, it's like a hit ratio or an odds ratio type of a thing, where that's how often this model, with the variables that have been retained, predicts group membership. So that's good. We're happy with that. That's a pretty good number. Stepping down here, variables in the equation. So what is it we're actually using? After all of these steps, we have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, plus a constant. So this last step down here. This is going to be the variate that's used to create the score, which would be what's G of X, which is then converted into a P of X, which is a percentage. Okie dokie. So yeah, so this is fantastic. I don't know. I haven't analyzed. I haven't even considered the significance and kind of why these specific variables do particularly well in explaining group membership. I would need a little theory probably. I'd need to really go back to the survey. I'd need to read what these were to clearly get a better picture of like why like this is company orientation or competitive orientation, question number 4. Uncertainty, question number 1. Risk aversion, question number 2. Innovation orientation, question 7 and 9, and then performance questions 3, 4, 9, and 10. I'd really want to go in and look at those probably, and kind of see how those were phrased and see if there's any synergy between them at all. When I do a factor analysis, these items would never come together. They would never fall together. They would never group together if I did a factor analysis. They'd make no sense. So it's this variable, though, that I created, this dummy variable, that seems to bring them together to help, maybe create a lot of explanatory power. And this is one of these things, we want our independent variables to explain the dependent variable, but we don't necessarily want our independent variables to covary together. So the fact that these are distinct, just weird, like a weird combination of variables, is probably a good thing. But we'd probably want to do a little bit more analysis to kind of see what's shaken out and why those are there. At any rate, we use this table here then to create our variant, the model then that we'll use to get our scores. The cut off then is 50% once the P of X is created, and then we kind of go from there. All right, anything else? There were some variables excluded as outliers. So again, we could kind of look at those a little bit more, but I'm not. So a case-wise list. These are individuals who may not be suitable to keep as outliers within the data set. So just jumping into this, if I go back into the data, nope, not that one. If we go back into the data here, you'll remember we saved some variables. So I'm going to go to the end of the data set, and I'm going to look at the last 2 columns, these guys here. And so the PRE1 is the probability that was created by the 9 variables that were selected by the process. And then the PGR is the group that it was assigned to. So again, we've got the estimated or assigned group, and then we have this here. Actually, this is actually kind of interesting. I should have, so the analysis, this is actually kind of interesting. So remember, validation is an important piece to this. So I'll step back 1 or 2 steps. Anything above a 0.5 is going to be a 1. Anything below a 0.5 will be a 0. So we have above a 0.5. So this is like the probability of them being a defender or a reactor is 54%, and they're classified a 1. And then we have this one here is less, so they're expected to be a prospector or analyzer, and so on and so forth, right? So that's where we get these group assignments based on the probability being above or below 0.5. Here's what's interesting, which I kind of forgot about, but I'm really glad I looked at. Remember, only 115 respondents gave us their group. So now what I could do is I could assign, because I'm doing this, I'm right about 80% of the time, or whatever that hit rate was, I could assign the companies a code for those who did not give me one. So remember, we got all these right here. If I move over and I look at the variable, the dependent variable that I had created, so I'm going to just cruise on back over here, and I'm going to get to my dependent variable that I had. Boom, right here, defender reactor. Oh crap, sorry, didn't mean to do that. Defender reactor, I'm looking at this column right here. These respondents, these first 25 respondents, didn't give me a grouping, right? But now that I've created the variant, I've predicted what group they'll be in. So I could impute their, I could put in here their predicted value, and then I could do further analysis on it. So that's actually kind of a cool application. So these first 25, I don't have an original like classification for, but because we created this variant, the software has assigned them, except for number 6, it looks like. The first 25, we've assigned the first 25 a number, and we could actually use that. So that's actually cool. I had forgotten that it would do that. And so we just created data, which is actually kind of neat. And, of those 25, if things all go well, it'll be accurate about 80%, 70 to 80% of the time. Now, can you live with that level of accuracy? I don't know. It's, this is not perfect. There's a lot of error here, but that's going to be a pretty good, like prediction rate probably for this particular data set that I've got. Okay, so let's see what else here. Let me just, yeah, that's not bad at all. We had, yeah, that's what's, that dog will hunt, as they say. It's not bad at all. All right, so so the homework assignment then, you use the same data for a discriminant analysis and then a logistic regression. And, again, this method here, we can hold out a sample, run the analysis if your sample size is large enough, and then validate the data or validate the variant by using the data that was held out. If you're using data dependent variables where you have more than 2 groups, you're using a discriminant analysis. And again, our goal here is to identify the variables that best explain group membership with the highest percentage of correctness. So that's how we validate, that's how we know whether the model's good or not. If you're not able to identify variables that help you increase that hit rate, then you need to do more work in identifying variables and measure. It's probably a measurement error or measurement issue, or you haven't thought about the theory behind what variables should predict group membership or not. Next week we'll do cluster analysis, and it's like the reverse, where we have variables and we don't have any groups identified yet, and we want to let the variables drive the formation of groups. So if you can kind of think about the reverse for next week, that's what cluster analysis will be all about, where we have like 500 customers, they all answered a survey. I'm going to take the questions that they were asked, and I'm going to use the questions to help form groups of customers. So like this whole identifying groups of customers is a little bit like identifying factors in factor analysis, only we're identifying dependent variables instead of groups of independent variables instead of groups of independent variables in that case. So it's kind of an interesting process. I think it's going to be something very, very useful for you moving into next week. So, we've been going at it now for what, about, I guess, a little over an hour and a half. This week, again, we're kind of just cruising along. I've posted the midterms. And again, generally speaking, they're pretty well done. I posted on Blackboard under the tab for the midterm. I posted an example exam for review. So within the comments, so on, and again, I'm a little fuzzy sometimes on what you yeah, the format that you see. So in Turnitin, I added comments to your submission. But then also there's, so throughout your submission, I added some comments for each question, and then a summary. And then also you can compare kind of what your, exam was to this one that's here, this exam for review. But again, I think generally speaking, everyone's in good shape as we kind of progress through the semester. Um, Please, if you've not given me your method topic, that's going to be, that assignment is coming up. Do you guys have any questions on the method assignment? Or any of the assignments for that matter? No? Okay. I assume that like no comments are good, that you guys are good, that everything's going okay. It's kind of interesting. I haven't received a lot of questions outside of class. So, I kind of go under the model that no news is good news. So I'm here though, and I want to be here if you guys have questions, or if there are things that I can help with, kind of as we go through here. So this week, again, discriminant analysis, logistic regression. Have fun with the assignment. Do you guys have any questions before we, kind of move forward? Are there things that I'm missing? All right. So, all right, I guess, again, the point of these sessions is strictly informational. And if, I just want to try to guide above and beyond what maybe the videos do. If that's helpful, then great. Let me know if you have any questions. Shoot me an email, give me a call or whatever. I hope everything else is going good. Again, it's hard to believe. So I guess we should say that we've got basically 2 weeks left after this week, and then we've got our exam. Just as a prep, I'll open up the exam here, probably in another week or so. Right now, just so you know, I'm developing the content for Manova because that's a new section for me. So I'm doing videos and I'm developing that material and the assignment for that. So it's not available yet, but I hope to get that knocked out this week. I'm partway through it now. But that'll be a new section that'll open up. So for our last content piece, Manova, but then for the final exam, you'll have a data set and you'll have a set of questions. You'll be doing analysis on the data. And the way that works that last week is we will identify one-on-one times to meet. It'll be on Zoom, of course, because we're not meeting face-to-face. And that schedule will be just we'll work out a schedule between us. There'll be about 45-minute time slots probably for that. And we'll talk about that more as we get closer to it. But the final exam, then the material will be available to you well in advance of the actual, when it's due. But that we'll just kind of go from there. Do you get any questions? All right. Let me know if you're sinking or swimming. If there's any problems, let me know. Until then, I guess we'll just we'll say goodbye, and we'll see you next week. Okay.
All right. Thank you.
Thank you.
You're welcome.
Thank you.
Have fun. Data's your friend.
Mm.
All right.
All right.